Okay, welcome everyone to another installation of final presentations in observational techniques and instrumentation in the Astrophysical Sciences and Technology PhD program. This is the first talk, and the speaker is Daniel Wysocki. He comes from the Rochester Institute of Technology in Rochester, New York. Dan?
All right, like you said, I'm Dan Wysocki, and I'm going to tell you a bit about the impact of the nonlinearity of the PL relation on distance measurements to Cepheid variable stars. So that's a mouthful, so I'm going to back up a little bit and give you a little bit of history and background on Cepheids. So, a classical Cepheid is a pulsating star. It exists in the instability strip of the HR diagram, and it's not in hydrostatic equilibrium. So, if we were to look at a Cepheid, if we observe it over time, we can see its brightness going up and down, and if we plot this, we get what's called a light curve. And on the right here, I have a sort of hand-wavy simulation of what that star might look like. And so you can see there's actually a relation between the radial velocity and the brightness. And this is kind of a simplistic model. There's a phase shift involved there that's not taken into account here. But this is sort of a rough approximation of what's going on in the star. So it's actually radially pulsating. And it's periodic. So some famous examples of Cepheids, first of all, Delta Cepheid, which is the Cepheid it was named after. Polaris, everybody knows Polaris, that's a Cepheid. And RS Pupus is actually one of the most interesting Cepheids because it's embedded in this nebula, and actually, if you observe it over time, you can watch the light propagate through. I don't have a video of it here, but you should look it up sometime. It's actually really interesting. So we didn't know that Cepheids were variable until the work of Edward, how do you pronounce that, Pigott, and John Goodricke. So in the 1780s, they were studying variable stars, not specifically Cepheids. They were actually looking for eclipsing binaries. That was their primary target, but they accidentally discovered that Cepheids were actually a different type of variable star. So Pigott was the first to discover that Eta Aquilae was a Cepheid, and then the next year Goodricke discovered that Delta Cepheid was a Cepheid. Of course, it wasn't named after the original, it was named after the second. So I mentioned the instability strip earlier. So here's an HR diagram, and this strip right here, as stars pass through that, that's called the instability strip. So during certain points in their lifetime, they will become unstable and begin to radially pulsate. And not all stars actually go through this phase, but Cepheids happen to be on this strip right here. And it's actually because of this that we get the period luminosity relation. So the reason for this is due to the kappa mechanism. So kappa here stands for opacity. And so what happens is, normally in a star, opacity decreases with temperature. But because of the helium-2 ionization zone, as it's contracting, it actually increases its temperature and opacity simultaneously. And so what this causes is a buildup of heat, which produces outward pressure. So it builds up a bunch of heat and then finally pushes its way out. And so this expands to the point of gravity exceeding the pressure, and then finally it begins to contract again. So this is the reason that it's not in hydrostatic equilibrium, because of this unbalance of the forces. Now, the main reason that Cepheids are useful is due to a discovery by Henrietta Swan Leavitt in the early 1900s. She was looking through the Harvard plates at images from the LMC and the SMC, and she was studying variability. And what she noticed was, if you plotted the period of oscillation versus the apparent magnitude for the Cepheids, you actually got a linear relation as long as you were in, well, actually it's a logarithmic relation. So the log of the period versus the magnitude will give you a straight line. And so she realized that from this property, we can actually measure their distances, because since there is a relation between the brightness, the intrinsic brightness, and the period, which we can easily measure on Earth, given enough time, we can actually tell the difference between the apparent magnitude and the absolute magnitude, and use that to compute the distance. And so that's called a standard candle. So if you can compute the absolute magnitude of something, you can observe its apparent magnitude, and from that you can get a distance modulus or a distance. So here's an example of the period luminosity relation in two different bands in the M101 galaxy. So that's the Pinwheel galaxy. So I have the V and I bands plotted here. And so you can see on the X scale, I have it in the log scale actually, you have the period in days. And on the Y-axis, you have the apparent magnitude. And I flipped magnitude, so up is brighter. And you can see that there's an increasing relation. So as the period gets longer, the apparent magnitude gets brighter. Now, Edwin Hubble used this to actually discover two major breakthroughs. He measured the distance to the Andromeda galaxy using Cepheids, and he thought it was 275 kiloparsecs, which isn't quite right. So even though that wasn't quite right, he did correctly realize that Andromeda was outside the Milky Way, and this basically revolutionized our view of the structure of the universe, because people had thought back then that the Milky Way was the universe, but in fact these so-called nebulas, or nebulae, were actually galaxies outside of our galaxy. And he also used Cepheids to calibrate his distance measurements, which contributed to his measure of the Hubble constant. So he used Cepheids to calibrate distances to other standard candles like supernovae, and was able to measure distances out to a very far scale. And by seeing how that related to redshift, he was able to determine H0, which is just the slope of distance versus redshift. And he estimated it was 500 kilometers a second per megaparsec. Now, Hubble's calibration of the period luminosity relation was not very accurate. And as we'll see, using modern estimates of these values, they were pretty far off. So his distance to the Andromeda galaxy was off by a factor of 2 or 3, and his estimate of Hubble's constant was completely off. It's closer to 67 than it is to 500. So that sort of emphasizes the importance of getting your calibration correct and taking into account things like, for instance, he didn't realize back then that there are what we now call classical and type 2 Cepheids. And so back then we thought they were all the same, and that caused a big disagreement between, or that caused a big miscalibration. Another smaller issue was the topic of this talk, which is the nonlinearity in the PL relation. So what people have found through statistical analyses is that there's actually a break in the linear relation around a period of 10 days. The mechanism for this is still under speculation. In fact, the existence of this is under speculation. Some people think it might be an observation error or something, but not actually intrinsic to Cepheids. So this is an active debate. So if we look here, this is a period luminosity relation with 3 different lines fit to it. The small dotted line is just assuming it's linear all the way through. And so you'll see that sort of best fits the entirety of this. However, if you fit a separate PL relation to the short period and the long period Cepheids, you get these two different lines. So for the short period, we have a higher slope, while for the long period, we get a lower slope. And so what that means, well, since we observationally are going to see more short period Cepheids, in part due to their abundance and in part due to the ease of observing them, it's going to be biased towards the short PL relation. So if you just fit them all as one, you're going to be strongly biased by all of these. Whereas if you fit them separately, you could recover this individual effect here. So what that really means is for long period Cepheids, we have a stronger, we have more of a deviation for the longer periods than for the shorter periods. And so if we restricted ourselves to looking at short period Cepheids, that might not be a big problem. But if we were to measure distances to long period Cepheids, that becomes a bigger problem, especially considering that longer period Cepheids are brighter, and therefore we can see them at further distances. So there was some statistical analysis done looking to see where this nonlinearity occurs, and they found a relation between temperature or wavelength and whether or not it was linear. And so they found at shorter wavelengths or cooler temperatures, it was very much nonlinear. But then around the K-band was where it transitioned between linear and nonlinear. And so for longer wavelengths, we actually get a linear relation. So that led to, in that same paper, that led to speculation that this was due to a hydrogen ionization front and photosphere interaction. And so essentially what happens is, depending on the period, the metallicity, and the phase in the pulsation, and the density, there may be an interaction between the hydrogen ionization front and the photosphere. And so in the case of the long period Cepheids, what they think happens is those two are interacting in a way that their temperature mixes, and so we don't get that difference in temperature, and that causes a flattening slope. But again, this is just speculation. There isn't really a consensus on the mechanism yet. So I wanted to answer the question of what are the implications on distance measurements by assuming that it's linear or nonlinear or whatever. And also, so obviously that has some impact on the Hubble constant, although to actually get enough data for that would not be within the scope of this course. And so I just looked at a single star. So I obtained some data. Actually, it's kind of a funny story. I originally obtained data from the Hubble Space Telescope on the Pinwheel Galaxy, and reducing that data ended up being kind of a headache because it was a crowded field. And so I was actually just yesterday given data by the AAVSO, and this ended up being much better data for this purpose. So this was a series of 189 V-band and 186 I-band images of T Mon, which is a Cepheid in the Monasteros constellation, and this data spanned over 2 years. And if you look at this field, it's pretty obvious there's really only one really bright star in here, and it's pretty easy to resolve, and so this made my job a lot easier. Now the FITS images were already bias and dark subtracted and flat fielded, but they had not been reduced to photometry, or at least I didn't use their photometry. So that's what I did. Now these images were taken by the Bright Star Monitor, which is an AAVSO small telescope. It's very modest if you look in this picture. Basically its goal is to observe the bright stars that nobody else really wants to look at with their fancy telescopes, because they would destroy their CCDs and their optics. So HST isn't going to look at TMON, but this little telescope is perfect for it. So I did some photometry. First I used the program Source Extractor to identify photometric sources, and then using the fluxes that it computed, I converted those to magnitudes with some arbitrary 0 point by dividing by the exposure time and taking the log of that. So here's just an example from one of those images. These are the sources that were extracted. And in this bright white dot, I've highlighted the source for TMON. And so you can see it's not a very crowded field. So from that, I did some differential photometry. And so basically, with Source Extractor, and just looking at FITS images, you don't know, if you're observing on one night and the sky's brighter, or whatever other factors come into play, you don't want to trust that the flux values for a given image are actually representative of the other images. And so there's a method called differential photometry, which essentially assumes that most of the stars aren't variable, and it uses a method to offset the 0 point for each image. So essentially it shifts the magnitudes for all the images so that they best agree, so that their sort of average brightness for the stars is equal. And so this gives you differential magnitudes, not magnitudes. But it saves the 0 point calibration for afterwards. And I actually used some software written by Dr. Richmond for doing this. So once you have that, you want to do a 0 point calibration. And so essentially what you do is you identify a number of non-variable stars in the field with known brightnesses. Now I was looking at SDSS, VI, and R band magnitudes. My original images are in V and I bands, but you can actually convert using Lupton's equations to I band. And so you do this for a number of stars, and then subtract the average offset to get calibrated magnitudes. Now, this is how it would work in theory. However, it didn't quite work as expected. Whenever I did this, my calibrating stars were always off by several magnitudes. Basically, I knew the mean magnitude of TMON, so I knew what to expect. It was about 8 magnitudes I was looking for, and I was getting on the order of 2 or 3. And so I believe something was wrong with my differential magnitudes, and I'm not entirely sure where that went wrong. So because of that, I couldn't get I couldn't go from my initial data to the final results I wanted, but I was able to go a bit further than this. So I was still able to obtain light curves, although with kind of unreasonable error bars on some of the points. So these are just the time in days versus magnitude. So the period has not been accounted for yet. So you would actually expect to see something like this, albeit not with such huge error bars. So once I have this data, I want to actually understand the underlying light curve. And so I did some data analysis. Now, what's traditionally done with variable stars, Cepheids in particular, is to do Fourier analysis. And so essentially what that means is you fit a Fourier series, which is just a sum of sinusoids or cosines. Now, the most general form of the Fourier series is an infinite series, although we don't actually use that. But in the general case, you have a mean magnitude, or a mean value. You have an amplitude for each of the cosines, you have a phase shift for each of the cosines. You have just a general angular frequency, and then each cosine has a wave number. And so essentially what happens is you increase the wave number in integral amounts, and what you get is, 1 angular frequency, 2 angular frequencies, 3. And so what that essentially does is take the wavelength, cut it in half, then cut it in thirds, then in fourths. And so you get all of these combination frequencies. So for a periodic light curve, obviously we don't use an infinite series, as I said. We want to use an nth order series, where n is some number that we choose. Now, this right here is a nonlinear equation. And so solving it would be pretty difficult. So using some trigonometry, we can break this cosine into a sine and a cosine term. And if you notice, this gets rid of the phase shift. And so all we have are 2 knowns, or actually 2n knowns. So we know what sine of k omega t is, and we know what cosine of k omega t is. And so this is actually a linear equation in terms of a naught, ak, and bk. And this is also another reason that the Fourier series is used, is because the parallels can be drawn between the fitted function and theoretical models for stellar pulsation. And so the fit parameters here can actually be useful in more than just fitting a line to a curve. Now, we do need to find the period first. So we can actually find this independent of the Fourier series. And there are a number of methods which fall into the category of periodograms. So Lohm-Scargill is the most commonly used, and actually I think it was actually developed for this purpose. And you can sort of think of it as a Fourier transform for sparse, unevenly sampled data. And so you have a time series, and you create a power spectrum for it, and at the peak you'll find the best period, or at least you hope. And so for a very well-behaved light curve, so I took this from Ogle, you get a nice sharp peak right where the best period is, and everything else is sort of, you see it's sort of symmetrical around here and then just flattens out. For not so nice data, like mine, you might get something that looks like this. So this was my I-band light curve, and this peak almost won, but luckily the true period, or very close to it, was actually the value that won out. For my V-band, I also got a similar effect. They're actually offset by about 0.05 days, but that's still pretty close. So using this periodogram, I was able to find the period. So after that, I need to fit a function to this light curve. And so we have a system of equations, like I said before. So for each magnitude, it depends on the time of observation and some other variables, which we're going to solve for. And so we can decompose this into a matrix equation, x times beta equals m. And so m are our magnitudes, which we know. X is this matrix, which represents the equations, and beta are unknown parameters. And so we're just going to solve for beta using linear regression. And so essentially what linear regression does is it says, find the parameters beta, which minimize the sum of the squares of the residuals. So you find the beta, which if you multiply it by your matrix X, it's going to give you predicted magnitudes, and then you take the difference, and that difference is your residuals, and then you take the sum over that squared, and that gives you your sum of square error. And so what least squares does is it finds the beta, which minimizes that error. And so if we actually write out this matrix equation, we actually get this right here. So it's just the sum of the Fourier series for each point minus the observed magnitude. So that's how we did this. But then there's also the question of how do you choose the order of the fit, n, the little n. So to do that, I used a method called grid search using cross-validation. So essentially what that does is it tries each value of n on some range, which I specified. And then for each n, instead of just fitting to that n, as long as you increase n, you're going to get a better fit. Except since it's noisy data, you don't want to actually fit the data points. You want to fit the underlying function. And so to approximate that, what we do is we leave out a portion of the data. And so instead of fitting it to all the data and then finding out the R squared or the goodness of fit based on those data, what we do instead is we leave out some percentage of the data. We fit the remainder, and then using that fit, we predict the ones that we left out. And so since those ones that we left out weren't involved in the fit, if our fit actually models the underlying function, it should be pretty good, right? And so we do that for each, if you did 10% left out, you would do each individual 10%, and then take an average over that. And so we do that for each value of n, and find the n with the best average R squared. And to do this, I used software which I helped develop. It's called Platypus. You can download it. It finds periods and it fits Fourier series, and it does a few other things. And you can download it today if you want. So after all that analysis, I arrived at some results. So here's a light curve in the I-band of my variable star. You'll notice the error bars are kind of strange. I used the uncertainties that were output by the differential photometry software. If I wanted more reasonable uncertainties, I'd have to go in and consider what we actually knew and what it was. Really, to get the best uncertainties on this, I'd have to understand exactly how that software worked and go back and also account for the uncertainties in the observations. But I didn't have time to do that. For the V-band, we have this. Now note, both of these I used the periods that I determined using a periodogram. But I also went on the internet and found sort of the standard, the period that AAVSO agrees on. So for the I-band, we get this. For the V-band, we actually get a really nice fit. I was actually surprised at how good this was. See, for Cepheids, there's kind of one of the telltale signs of a Cepheid is this sort of shark fin shape to the light curve. Not all of them are like that, but if you see something like that, it's probably a Cepheid. And so using my period, it was kind of it wasn't quite a shark fin, but using the correct period, which was only off by 0.07, I think, days, you get this nice fit. So it's at least reassuring that even if something was off, it was still good enough to get this. So I wrote down the Fourier coefficients that were output by this. It was an 8th order fit. You'll notice the uncertainty in the average magnitude is it's actually greater than the value of it, so it's definitely not to be trusted. So if I had been able to correctly calibrate my 0 point, I would have been able to obtain apparent magnitudes. And I did obtain periods. And from that, I could calculate distances. However, since I wasn't able to calibrate the 0 point, I went and looked up some values which AAVSO cites. So they're both around 5 and 6 magnitudes in the V and I bands. Then I looked up some period luminosity and Wesen height relations. So here we have the period luminosity relation, which assumes that it's linear. And below that we have only for the long periods. So it assumes it's nonlinear and takes only periods greater than 10 days. Then we also have what's called the Wesson-Height relation, which combines period and color, and is actually from some analysis that was cited, I don't know if it was in this paper, but it was another paper by them. It's actually linear, and so this would actually be a perfect relation. So I actually ran out of time to calculate this, although I could do it if I had a half hour of time. Basically, all I would have to do is substitute in the V and I band magnitudes, or really, I would just have to substitute in the periods that I found and the V and I band magnitudes here, and take an offset on these from the LMC, and I would be able to obtain distance moduli. So if I were to do that, my next step would be to compare it with the literature, and also to compare it with parallax distance, which I found here is 1.21 milliarcseconds. So that's actually one of the nice features of this star, is that there is a known parallax. Some other future works, I would need to correct for extinction. Timon is actually close to the galactic plane, so there's a lot of reddening. And really, to understand the impact of this distance relation, or of this miscalibration, you would need to do some statistical analysis for a number of stars and not just one. And another thing would be to consider the metallicity dependence on the PL relation. So this is an area of active debate, but that would be another miscalibration in the relation. And that's it. Does anyone have any questions?
Which magnitude system which magnitude system are you using, and which magnitude system of the literature that you used to compare your?
So they were using Johnson BMI band magnitudes.
Okay.
Yeah.
Other questions?
Yeah.
Oh, sorry.
Yeah, I just wanted, like, this is maybe just more like comments rather than questions. So if your value is off, like, it seems like your value is just offset from the magnitude that you expected. Right?
Well, that's what I expected to be. Like,
so if that's the case, you may want to check like how you transform like the magnitude from I or R from one filter to another. Since I know that different type of filter have different equations.
So the only thing is I didn't even get to that point because I was just looking at the V-band magnitudes for the offsets, and since those were a direct translation, the fact that they were off by like 3 or 4 magnitudes was just a telltale sign that something was off. I think it's actually more than just an offset, and also a scaling, like inter-magnitude scaling, that something's off there.
Okay.
If you go to one of your first plots where you showed you data, which had
Oh,
really large
actually,
data.
that reminds me of something I missed. So in this data here, you'll notice for the, what was this, the I band, you get coverage over basically the entire, actually this one was a shorter time scale. This is only 180 days. But you get coverage over the entire time span. Whereas for the V band, there's this huge gap. Like there's one data point up here and then nothing, and then finally data points. And I went and looked back, and actually, this was just a selection. The differential photometry software was actually flagging these. There was data all throughout here, and it was being flagged as bad data. And so that might be another sign that something was off.
So was it being flagged as bad data because of the error bars? Because also about the error bars, is it that half of your points have really large error bars, whereas half of them don't have large error bars?
I think so. Let me look at these. It seems like it's about 50-50, but it's hard to tell just from the graph. but you can see like there's ridiculously small error bars and then ridiculously large error bars. It's almost like there's two categories, like good and bad, which is another reason why I need to go back and do it myself and not use what's output by this program.
Do you know for sure at the start you used 5 to 0 points and not either like visible, variable or something weird?
Well,
Like,
I
do
mean,
you
I
know
looked
why
at a
at the
number.
start you used
I
calculate?
looked at a number of them, and they were all off by, like they were all offset by about 2 or 3 magnitudes, whereas I was expecting 8.
No, I mean like when you, like, so I assume those error bars is from your program. So do you know where at the start you used to calibrate are not variable?
For the differential photometry?
Yeah.
Well, the thing is, there can be variable stars in the sample, as long as they're not the majority. So, it's, I mean, maybe it's not, I think it's a safe
maybe
assumption.
some of them affect that.
Yeah, but I think maybe I think it's a safe assumption to say that most of them aren't variable, just because most stars aren't very variable. If there were a few, it might contaminate the sample, but
So
I
this
mean, that would
seems
be
to be
worth-
something very periodic. Maybe you happen to have something that also have the same period or something, and they get resonance, I don't know. But the error bars seem very periodic.
yeah. Or it might also have to do with the magnitude, the fact that it was at fainter magnitudes where you get more of the error bars like that. If you notice, it's at the peak where you get the least error bars. And I have the axis flipped, so up is brighter.
Do you have any more questions? Or I had a few questions.
Sure.
So going back from the beginning, what's your science question and did you answer it?
So I was not quite able to answer my science question because my ultimate question was how strong was the impact of the uncertainty caused by whether you use one relation or the other. Because in the literature, actually most people use the linear relation despite knowing that this nonlinear relation exists.
Okay.
And it's mostly because it's so much easier to do the linear way. So my question was ultimately to see if we could measure the impact on one star. But since I didn't actually get through the photometry, I wasn't able to do that.
Okay. Another one, how was the period luminosity relation calibrated?
How was it calibrated?
Yeah.
The ones that I showed.
No, historically, how was it calibrated? Because Levitt just noticed that there was some sort of relationship, but she didn't
Yeah.
calibrate it.
I'm not entirely sure which Cepheid they used. It might have been Polaris because it's the closest, but I'm not sure which Cepheid they used. But they
But
did
maybe
use,
looking at a close by
Yeah,
star and then
yeah.
using parallax or something. Where
Yeah,
you-
that's still what we do today.
Yeah.
For the most part.
What's a W Virginis star?
W Virginis. I'm not entirely sure. I mean, I think it's another type of variable. Is that it?
It's a type 2 Cepheid.
Oh, it's a type 2 Cepheid. Okay.
Yeah.
Yeah.
What are those? You only looked at type 1s?
Yeah, I only looked at type 1s. When I say classical Cepheid, that's type 1 Cepheid.
What's the difference between type 1 and type 2?
I mean, they're completely different types of stars, and you can see their period luminosity relations here are pretty offset.
Physically, what's different?
I'm not actually sure. I don't know much about type 2 Cepheids.
Okay. Go to 39.
Well, I do know they're different populations, so I think type 2 are population 2.
Yeah, that's it. It's the metallicity.
Okay.
And it's the age. Go to 39.
39. Yes.
No, I got the wrong slide. Go back one.
Sit down.
It's the figure. Go to the one with the figure. Right there. What are all those little secondary peaks?
Well, so the thing is, you can sort of think of it as, while there is an ideal period, if you were slightly off from that, you might get something that's close.
So you might have to interrogate the data a little bit more to figure out exactly why those are coming in.
Yeah, but that's, I mean, it's something you get even with really good data. But when it's really good, it sort of, you know, knocks down the strength of those.
Go to 45. Yeah, is there a solid curve that I'm seeing there, a black line?
Yeah, that's my
What is
fit.
that black line? That's your fit?
Yeah, it's my fit.
Okay. And then you have tiny error bars in the one place, big error bars in the other place, right? Okay, that's all I have. Were there any other questions? Okay, right here.
So, can you go to the slide with the argument?
The one, oh,
I think it's 38.
yes?
Yeah. So why do you want to use like the sum of on your residual instead of like the mean residual? Because what if you have a really good fit but a few
Well,
bad data points?
So that's why you would want to do weighted regression. And since I didn't have reliable weights, since I didn't have reliable errors, I couldn't actually do that. So you're saying just pick the best data point, or?
Well, I mean, what you say you said you
So
take
this
the
is-
sum of the residual.
Right, so the residual for each data point.
Mhm.
So it's it's basically just finding the curve that fits all the data points the best, right?
So why would you want the sum instead of say the mean or the median of the residual? Because what if you have a really good fit and then you have like a few bad data points and that throw up the sum of the whole thing? Like
I'm
you
not
said
sure.
a bunch of small number and then a few
I'm not sure what you
really
mean by the
big
mean
numbers.
residual, like.
Since you said
Oh.
that you find a residual for each point, right?
Well, so the thing is, you don't actually calculate it this way. Like, this is what it accomplishes. So, if you're trying to find the thing that minimized the mean residual,
Mhm.
that might be a much harder problem to solve. Like, linear regression is just a simple matrix operation. But to do something like that might require something a lot more involved.
Well, what I'm thinking is just you find a fit and then you find the residual for all of the data points using that fit. And then you do it again and you have the second fit and then you find a residual for that fit. So what I'm thinking is you are comparing the residual for the two fits. So from this one, what I understand is that you sum all of the residual for each data point for one fit and you compare it with the same quantity for the second fit. Why do you want to take the sum instead of the
No,
median?
you're just doing one, like, this is how you get the fit. Like, there isn't a number of iterations like that. It's just, like, this is what's accomplished by that matrix operation, essentially. But it's not like I'm fitting it, then taking the residuals, and fitting it and taking the residuals. It's, like, the residuals are sort of implicit in the matrix operation.
But I think there's a generic question, how best to fit data.
Yeah.
What kind of routine to use, chi-square fitting, or
Yeah.
means, or outliers, weighting by the inverse of the error,
Yeah.
which is another technique.
Yeah.
That's all we have time for now. Let's thank Dan.